Hello guys, welcome back. Today what we're going to learn is called rational function.
When we first started learning about fractions or rational numbers, we learned about the idea of putting things in lowest terms. So if we saw something like 3, 6, we knew that 3 and 6 share a common factor. We know that the numerator, well, 3 is just 3, but that 6 could be written as 2 times 3. And say, since they share a common factor, the 3 in this case, we could divide the numerator by 3 and the denominator by 3, or we could say that this is just 3 over 3, and they would cancel out. And in lowest terms, this fraction would be 1/2. Or, just to kind of hit the point home, if we had 8 over 24. Once again, we know that this is the same thing as 8 over 3 times 8, or this is the same thing as 1 over 3 times 8 over 8. The 8's cancel out, and we get this in lowest terms as 1/3. The same exact idea applies to rational expressions. These are rational numbers, rational expressions.
Okay, one thing to keep in mind is that this is not rational. It's called rational. Rational. Read it again. Rational.
Applies to rational expressions. These are rational numbers. Rational expressions are essentially the same thing, but instead of the numerator being an actual number and the denominator being an actual number, they're expressions involving variables. So let me show you what I'm talking about. Let's say that I had 9x plus 3 over 12x plus 4. Now this numerator up here, we can factor it. We can factor out a 3. This is equal to 3 times 3x plus 1. That's what our numerator is equal to. And our denominator, we can factor out a 4. This is the same thing as 4 times 3x. 12 divided by 4 is 3. 12x over 4 is 3x. Plus 4 divided by 4 is 1. So here, just like there, the numerator and the denominator have a common factor. In this case, it's 3x plus 1. In this case, it's a rational, it's a variable expression. It's not an actual number, but we can do the exact same thing. They cancel out. So if we were to write this rational expression in lowest terms, we could say that this is equal to 3 over 4. That's equal to 3 over 4. Let's do another one. Let's say that we had x squared. Let me see a good one. So let's say we had x squared minus 9 over 5x plus 15 over 5x plus 15. So what is this going to be equal to? So the numerator, we can factor. It's a difference of squares. We have x plus 3 times x minus 3. And in the denominator, we can factor a 5 out. So this is 5 times x plus 3. So once again, a common factor in the numerator and in the denominator, we can cancel them out. But we touched on this a couple of videos ago. We have to be very careful. We can cancel them out. We can say that this is going to be equal to x minus 3 over 5. But we have to exclude the values of x that would have made this denominator equal to 0. That would have made the entire expression undefined. So we could write this as being equal to x minus 3 over 5. But x cannot be equal to negative 3. Negative 3 would make this 0, or it would make this whole thing 0. So this and this whole thing are equivalent. This is not equivalent to this right here, because this is defined at x is equal to negative 3, while this isn't defined at x is equal to negative 3. So to make them the same, I also have to add the extra condition that x cannot equal negative 3. And so likewise over here, if this was a function, if this was, let's say this was, we wrote y is equal to 9x plus 3 over 12x plus 4, and we wanted to graph it. When we simplify it, the temptation is, oh, well, we factored out a 3x plus 1 in the numerator and the denominator. They cancel out. The temptation is say, well, this is the same graph as y is equal to the constant 3/4, which is just a horizontal line at y is equal to 3/4. But we have to add one condition. We have to exclude the x values that would have made this thing right here equal to 0. And that would have been 0 if x is equal to negative 1/3. If x is equal to negative 1/3, this or this denominator would be equal to 0. So even over here, we'd have to say x cannot be equal to negative 1/3. That condition is what really makes that equal to that. That x cannot be equal to negative 1/3. Let's do a couple more of these, and I'll do these in pink. Let's say that I had x squared plus 6x plus 8 over over x squared plus 4x. Or actually even better. Let me do this a little bit. X squared plus 6x plus 5 over x squared minus x minus 2. So once again, we want to factor the numerator and the denominator, just like we did with traditional numbers when we first learned factoring, when we first learned about fractions and lowest terms. So if we factor the numerator, what two numbers, when I multiply them equal 5, and I add them equal 6? Well, the numbers that pop into my head are 5 and 1. So the numerator is x plus 5 times x minus 1. And then our denominator, two numbers, multiply -2, add them -1. -2 and +1 pop out of my head. This is a +1, right? X plus 5 times x plus 1, right? 1 times 5 is 5. 5x plus 1x is 6x. So here we have we have a +1 and a -2. So x minus 2 times x plus 1 times x plus 1. So we have a common factor in the numerator and the denominator. These cancel out. So you could say that this is equal to x plus 5 over x minus 2. But for them to really be equal, we have to add the condition. We have to add the condition that x cannot be equal to -1. We cannot, because if x is equal to -1, this is undefined. We have to add that condition because this by itself is defined at x is equal to -1. You could put -1 here and you're going to get a number. But this is not defined at x is equal to -1. So we have to add this condition for this to truly be equal to that.
So what do we have now? We know that how can we reducing the rational expression by cancel out some items in its numerator and numerator. Okay, what is end behavior of rational functions?
So we're given this function f of x, and it equals this rational expression over here. And we're asked, what does f of x approach as x approaches -infinity? So as x becomes more and more and more and more negative, what does f of x approach? And like always, pause the video and see if you can think about that on your own. Well, one thing that I like to do when I'm trying to consider the behavior of a function as x gets really positive or really negative is to rewrite it. So f of x, I'm just rewriting it once, is equal to 7x squared minus 2x over 15x minus 5. Now, an interesting technique to think about what happens to the different terms as x gets very positive or x gets very negative is to divide both the numerator and the denominator by the highest.
Before we go on, I just want to point out a mistake he made. Apparently, here should be an 8 sign. Did you notice that?
Highest degree term of x in the denominator. And the highest degree term of x in the denominator is the first degree term. We have just a single x there. So let's multiply both the numerator and the denominator by 1 over x. Or another way of thinking about it is we're dividing both the numerator and the denominator by x. And if we're doing the same thing to the numerator and the denominator, if we're multiplying or dividing them by the same value, I should say, well then I'm just really just multiplying it by 1. So I'm not changing its value. But this will make it a little bit more interesting and a little bit easier for us to think about what happens when x becomes very, very, very negative. So 7x squared divided by x, or being multiplied by 1 over x, is going to be 7x. 2x times 1 over x, or 2x divided by x, is just 2. And then all of that over 15x divided by x, or 15x over x, is just going to be 15. And then you have 5 over x. 5 times 1 over x is equal to 5 over x, minus 5 over x. Now this is equivalent for our purposes to what we started with, but it makes it a little bit easier to think about what happens when x gets very, 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 very negative. Well, when x gets very, 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 very negative, this is going to become a very large negative number. You subtract 2 from it, it really won't matter much. You divide that by 15, well, that's not going to matter much. And this is just going to become very, very, very small. You're taking 5 and you're dividing it by ever larger negative numbers, or more and more negative numbers. So this right over here is going to go to 0. This thing over here is going to go towards infinity. And if you, or I should say it's going to go towards negative infinity. 7 times, for 7 times a negative trillion, 7 times the negative Google, 7 times the negative Google Plex. We're getting more and more negative numbers. This is going to approach negative infinity. It doesn't matter that you're subtracting 2 from that. In fact, that'll get even more negative. It doesn't matter if you then divide that by 15. You're still approaching negative infinity. If you had an arbitrarily negative number you divide by 15, you still have an arbitrarily negative number. And so you could say that this is going to go to negative infinity. Now, another way that you could have thought about it, and this is actually how I do think about it when I'm trying to when I see these types of problems, I say, well, which terms in the numerator and the denominator are going to dominate? And what do I mean by dominate? Well, as x gets very positive or x gets very negative, another way to think about it is as the magnitude of x gets large, the absolute value of x gets large, the higher degree terms are going to grow much faster than the lesser degree terms. And so we could say that for large x, for large x, and when I say large, I mean high absolute value. High absolute value. And if we're going to negative infinity, that's high absolute value. So f of x is going to be approximately equal to the highest degree term on the top, which is 7x squared, divided by the highest degree term on the bottom. 15x is going to grow. In fact, this is right over here is constant. So as this becomes larger and larger and larger, this is going to matter a lot less. So it's going to be approximately that, which is equal to 7x over 15. Well, even here, think about what happens when x becomes very, very negative here. Well, you're just going to get larger, you're going to get more and more and more negative values for f of x. So once again, f of x itself is going to go to negative infinity as x goes to negative infinity. Let's do another one of these. So here they're telling us to find the horizontal asymptote of q. And you could find a horizontal asymptote. You could think about it as what is the function approaching as x approaches infinity or as x approaches negative infinity. And just as a couple of examples here, it's not necessarily the one q of x that we're focused on, but you could imagine a function, let's say it has a horizontal asymptote at y is equal to 2. So that's y is equal to 2 there. Let me draw that line. So let's say it has a horizontal asymptote like that. Well, then the graph could look something like this. Let me draw a couple of them that have horizontal asymptotes. So maybe it's over here, it does some stuff, but as x gets really large, it starts approaching, the function starts approaching that y equals 2 without ever quite getting there. And it could do that on this side as well as x becomes more and more, negative. As it gets more negative, it approaches it without ever getting there. Or it could do something like this. You could have, if it has a vertical asymptote too, it could look something like this, where it approaches the horizontal asymptote from below as x becomes more negative, and from above as x becomes more positive, or vice versa. So this is just a sense of what a horizontal asymptote is. It's really what's the behavior, what value is this function approaching as x becomes really positive or x becomes really negative. Well, let's just think about it. We could essentially do what we just did in that last example. What happens if we were to divide all of these terms by the highest degree term in the denominator? Well, if we divide, the q of x is going to be equal to, the highest degree term in the denominator is x to the 9th power. So we could say 6x to the 5th divided by x to the 9th is going to be 6 over x to the 4th, and then minus 2 times x to the 9th, all of that over 3 over, I'm going to divide this by x to the 9th, x to the 7th plus 1. Well, if x approaches positive or negative infinity, 6 divided by arbitrarily large numbers, that's going to go to 0. 2 divided by arbitrarily large numbers, whether they are positive or negative, that's going to go to 0. So your numerator is clearly going to go to 0. This term of the denominator, 3 divided by arbitrarily large numbers, whether we're going in the positive or the negative direction, it is going to approach 0. It'll approach 0 from the negative direction if we're approaching, or we could say from below if we're dealing with very negative x's. If we're dealing with very positive x's, then we're going to approach 0 from above. We're going to get smaller and smaller positive values. So all of these things go to 0, and this right over here would stay at 1. And so if you're approaching 0 in your numerator and approaching 1 in your denominator, the whole thing is going to approach 0. So in the case of q of x, you have a horizontal asymptote at y is equal to 0. I don't know exactly what the graph looks like, but we could draw a horizontal line at y equals 0, and it would approach it from above or below. Let's do one more. What does f of x approach as x approaches negative infinity? Well, let's divide all of these terms by the highest degree that we see in the denominator. We see an x to the 4th. So 3x to the fourth divided by x to the fourth is 3 minus 7 over x squared. I'm just dividing by x to the fourth. Minus 1 over x to the fourth over x to the fourth divided by x to the fourth is 1 minus 2 over x plus 3x to the fourth. This is an equivalent. This right over here is, for our purposes, for thinking about what's happening at kind of an end behavior as x approaches negative infinity, this will do. I've just divided everything by x to the fourth. And so what's going to happen as x approaches negative infinity? This is going to approach 0. This is going to approach 0. This is going to approach 0, and this is going to approach 0. And so as all of that stuff approaches 0, what we're left with is we're going to approach 3 over 1, or we could say just 3. Another way you could think about doing these is look at the highest degree terms, 3x to the fourth, x to the fourth. Ignore everything else because they're going to be overwhelmed by these higher degree terms. So you could say f of x is approximately equal to 3x to the fourth over x to the fourth for large magnitude x. And very negative is still a very large magnitude, large absolute value. And so 3x to the fourth divided by x to the fourth, f of x is going to be approximately equal to 3, or it's going to approach 3. So that's another way that you could think about it.
Okay, quite interesting. So by watching this video, at least we have learned about how can we plan out the end behavior. Here, the end behavior means that if you put an infinite number in as the input to that function, what kind of output you would get. Sometimes it's infinity. At some other case, it might be a constant number.
Discontinuities of rational functions.
Discontinuities of rational functions.
So we have this function f of x expressed as a rational expression here, or defined with a rational expression. And we're told that each of the following values of x, select whether f has a 0, a vertical asymptote, or a removable discontinuity. And before even looking at the choices, what I'm going to do, because you're not always going to have these choices here, sometimes you might just have to identify the vertical asymptotes, or the zeros, or the removable discontinuities, is I'm going to factor this out, and hopefully, or I'm going to factor the numerator and the denominator to hopefully make things a little bit more clear. And we're going to think about what x values make the numerator and or the denominator equal to 0. So the numerator, can I factor that? Well, let's see. What two numbers, their product is negative 24, and they add to negative 2? Let's see, that would be negative 6 and positive 4. So we could write x minus 6 times x plus 4. Did I do that right? Negative 6 times 4 is negative 24. Negative 6x plus 4x is negative 2x. Yep, that's right. All right. And now in the denominator, let's see, 6 times 4 is 24, 6 plus 4 is 10. So we could say 6x plus 6 times x plus 4. So let's look at the numerator first. The numerator, 0, if x is equal to positive 6 or x is equal to negative 4. The denominator is 0 if x is equal to negative 6 or x is equal to negative 4. So let's think about it. Can we simplify this, what we have up here, a little bit? And we're just going to keep in mind what I just wrote down. Well, it might be just jumping out at you. You have an x plus 4 divided by an x plus 4. Why can't we simplify this expression a little bit and just write this whole thing, right? Our original expression as being x minus 6 over x plus 6, where x, if we want it to be algebraically equivalent, we have to constrain the domain where x cannot be equal to negative 4. Well, this is interesting because before, when x equals negative 4, we had all this weird 0 over 0 stuff, but we were able to remove it, and we were able to make it just kind of this extra condition. And if you were to graph it, it would show up as a little bit of a removable discontinuity, a little bit of a point discontinuity. It's just one point where the function is actually not defined. So in this situation, and this is typical where there's a thing that you can factor out, it was making the numerator and the denominator equal 0, but you can factor that out so it no longer does it. That's going to be a removable discontinuity. So x equals negative 4 is a removable discontinuity. And once you've factored out all of the things that would make it a removable discontinuity, then you can think about what's going to be a 0 and what's going to be a vertical asymptote. Once you've factored out everything that's common to the numerator and the denominator, if of what's left something makes the numerator equal to 0, well then it's going to make this whole expression equal to 0, and so you're dealing with a 0. So at x equals 6, 6 would make the numerator equal to 0. 6 minus 6 is 0. So there you're dealing with a 0. And to make the denominator equal to 0, you get x equals negative 6. x. That would make the denominator equal 0. So that's a vertical asymptote. And it's called a vertical asymptote because as you approach this value, as you approach -6, either from values smaller than -6 or larger than -6, the denominator is going to become either it's either going to become a very small positive number or a very small negative number. It's going to approach 0 either from above or below. And so when you divide by that, you're going to get very large positive values or very large negative values. And so your graph does stuff like that. So you have a vertical asymptote. It might either do something like that, or it might do something like this, where this is your vertical asymptote, and then when you approach from here, it bumps up like that. So either way. So that's why that's a vertical asymptote. Let's do another one. All right. So same drill, and like before, and always pause the video and see if you can work it out on your own. Let me factor it. So let's see, two numbers, the product is -32, they're going to have different signs, 8 and 4, and then we want the larger one to be positive since they have to add up to positive 4x. So x plus 8 times x minus 4. Yep, I think that's right. And then divided by, this is 4 times 4 is 16, -4 plus -4 is -8. So this is x minus 4 times x minus 4. Now this is really interesting because you might say, oh, I have an x minus 4. Maybe x equals 4 is a removable discontinuity. And it would have been unless you had, if you didn't have this over here, because x equals 4, even after you factor this, you still can't, it's the expression, the function is still not going to be defined when x equals 4. And so this function is actually equivalent to x plus 8 over x minus 4. I don't have to put that extra little constraint like I did before. I don't have to put this little constraint that describes this removable discontinuity because that constraint is still there after I've canceled out this x minus 4 with this x minus 4. And so here this is actually an algebraically equivalent expression to this one right over here. And so now we can think about what the zeros or the vertical asymptotes or the removable discontinuities are going to be. Well, something that makes the numerator 0 without doing it to the denominator is going to be a 0. And x equals -8 makes the numerator equal to 0 without doing anything without making the denominator equal to 0. It would make the denominator equal to -12. So you can literally just evaluate h of -8 is equal to 0 over -12, which is equal to 0. So that's why we call it a 0. What about x equals 4? Well, x equals 4 is going to make the denominator only equal to 0. And so that's going to give us a vertical asymptote. And we're all done.
One thing to notice here is that when the x equal to 4, no matter what kind of situation, no matter what happened, the y is not undefined. So in that case, it means that x can never be equal to 4. But it can be equal to any other values than 4. Graphs of rational functions.
So we have f of x is equal to 3x squared minus 18x minus 81 over 6x squared minus 54. Now what I want to do in this video is find the equations for the horizontal and vertical asymptotes. And I encourage you to pause the video right now and try to work it out on your own before I try to work through it. So I'm assuming you've had a go at it. So let's think about each of them. So let's first think about the horizontal asymptote. See if there at least is one. So the horizontal asymptote is really what is the line, the horizontal line that f of x approaches as the absolute value of x approaches infinity. Or you could say, what does f of x approach as x approaches infinity? And what does f of x approach as x approaches negative infinity? So there's a couple of ways you could think about it. Let me just rewrite the definition of f of x right over here. So it's 3x squared minus 18x minus 81, all of that over 6x squared minus 54. Now there's two ways you could think about it. One, you could say, okay, as the absolute value of x becomes larger and larger and larger, the highest degree terms in the numerator and the denominator are going to dominate. The numerator and the denominator are going to dominate. And so what are the highest degree terms? Well, in the numerator you have 3x squared squared, and in the denominator you have 6x squared. So as the absolute value of x approaches infinity, these two terms are going to dominate. F of x is going to become approximately 3x squared over 6x squared. These other terms are going to matter less. Obviously, minus 54 isn't going to grow at all, and minus 18x is going to grow much slower than the 3x squared. The highest degree terms are going to be what dominates. And if we look at just those terms, then you could think of simplifying it in this way. So that's f of x is going to get closer and closer to 3/6 or 1/2. So you could say that there's a horizontal asymptote at y is equal to 1/2. Another way we could have thought about this, if you don't like this whole little bit of hand-wavy argument that these two terms dominate, is that we can divide the numerator and the denominator by the highest degree, or x raised to the highest power in the numerator and the denominator. So the highest degree term is x squared in the numerator, so let's divide the numerator and the denominator, or I guess you could say the highest degree term in the numerator and the denominator is x squared. So let's divide both the numerator and denominator by that. So if you multiply the numerator times 1 over x squared and the denominator times 1 over x squared, notice we're not changing the value of the entire expression. We're just multiplying it times 1 if we assume x does not equal 0. And so we get to, so in our numerator, let's see, 3x squared divided by x squared is going to be 3 minus 18 over x minus 81 over x squared. And then all of that over 6x squared times 1 over x squared, that's just going to be 6. And then minus 54 over x squared. So what's going to happen? If you want to think in terms of, if you want to think of limits as something approaches infinity, so if you want to say the limit as x approaches infinity here, what's going to happen? Well, this, and that are going to approach 0, so you're going to approach 3/6 or 1/2. Now, if you said as x approaches negative infinity, it would be the same thing. This, and this approach 0, and once again, you approach 1/2. So that's the horizontal asymptote. Y is equal to 1/2. Now let's think about the vertical asymptotes. So let me write that down right over here. Let me scroll over a little bit. So vertical asymptote, or possibly asymptotes. Vertical, maybe there is more than one. Now, it might be very tempting to say, okay, you hit a vertical asymptote whenever the denominator equals 0, which would make this rational expression undefined. And as we'll see for this case, that is not exactly right. Just making the denominator equal to 0 by itself will not make a vertical asymptote. It will definitely be a place where the function is undefined, but by itself, it does not make a vertical asymptote. So let's just think about this denominator right over here. So we can factor it out. Actually, let's factor out the numerator and the denominator. So we can rewrite this as f of x is equal to, the numerator is clearly every term is divisible by 3. So let's factor out a 3. It's going to be 3 times x squared minus 6x minus 27. All of that over the denominator, each term is divisible by 6. 6 times x squared minus 9. And let's see, we can factor the numerators and denominators out further. So this is going to be f of x is equal to 3 times, let's see, two numbers, their product is negative 27, their sum is negative 6, negative 9 and 3 seem to work. So you could have x minus 9 times x plus 3, just factor the numerator, over the denominator. This is the difference of squares right over here. So this would be x minus 3 times x plus 3. So when does the denominator equal 0? So the denominator equals 0 when x is equal to positive 3 or x is equal to negative 3. Now, I encourage you to pause this video for a second. Think about, are both of these vertical asymptotes? Well, you might realize that the numerator also equals 0 when x is equal to negative 3. So what we can do is actually simplify this a little bit, and then it becomes a little bit clearer where our vertical asymptotes are. So we could say that f of x, we could essentially divide the numerator and denominator by x plus 3, and we just have to keep, if we want the function to be identical, we have to keep the caveat that the function itself is not defined when x is equal to negative 3. That definitely did make us divide by 0, so we have to remember that, but that will simplify the expression. function. So this exact same function is going to be, if we divide the numerator and denominator by x plus 3, it's going to be 3 times x minus 9 over 6 times x minus 3 for x does not equal negative 3. Notice, this is an identical definition to our original function, and I have to put this qualifier right over here for x does not equal negative 3 because our original function is undefined at x equals negative 3. X equals negative 3 is not a part of the domain of our original function, and so if we take it out, like if we take x plus 3 out of the numerator and denominator, we have to remember that. If we just put this right over here, this wouldn't be the same function because this without the qualifier is defined for x equals negative 3. But we want to have the exact same function. So you'd actually have a point discontinuity right over here, and now we could think about the vertical asymptotes. Now the vertical asymptote is going to be a point that makes the denominator equal 0, but not the numerator equal to 0. X equals negative 3 made both equal 0. So our vertical asymptote, I'll do this in green just to switch, or blue. Our vertical asymptote is going to be at x is equal to positive 3. That's what made the denominator equal 0, but not the numerator. So let me write that. The vertical asymptote is x is equal to 3. And so using these 2 points of information, or I guess what we just figured out, you can start.
Alright, so from this video we know that if for whatever inputs we always get a constant output, then that means that's the horizontal asymptote. Did I read it wrong?
Asymptotes.
Asymptotes. This is one situation. Where we have another situation where if you can make the denominator undefined, that's why if you can make the denominator undefined while keep the numerator defined, then for that value you could say that it's a vertical asymptote because the x value or the input can never be that.
Start to attempt to sketch the graph. This by itself is not going to be enough. You might want to also plot a few points to see what happens, I guess, around the asymptotes as we approach the 2 different asymptotes. But if we were to look at,
They call it asymptote. That's really hard to read.
The asymptotes as we approach the 2 different asymptotes. But if we were to look at a graph, actually let's just do it for fun here, just to complete the picture for ourselves. The function is going to look something like this. It's going to look something like this, and I'm not doing it at scale. So if that's 1, and this is 1/2 right over here, y equals 1/2 is the horizontal asymptote. Y equals 1/2 is a horizontal asymptote. Y is equal to 1/2. And we have a vertical asymptote at x is equal to positive 3. So we have 1, 2, I want to do that in blue. 1, 2, 3. Once again, I didn't draw it to scale, or the x and y's aren't on the same scale. But we have a vertical asymptote just like that. But just looking at this, we don't know exactly what the function looks like. It could look like something like this. And maybe it does something like that, or it could do something like that, or it could do something like that and that, or something like that and that. So hopefully you get the idea here. And to figure out what it does, you would actually want to try out some points. And the other thing we want to be clear is that the function is also not defined at x is equal to negative 3. So if this is, let me make x equals negative 3 here. So x equals negative 3. So 1, 2, 3. So the function might look, and once again, I haven't tried out the points, it could look something like this. It could look something where we're not defined at negative 3. We're not defined at negative 3. And then it goes something like this, and maybe it does something like that, or maybe it does something like that. It's not defined at negative 3, and this will be an asymptote right now, so it'll get closer and closer. And it could go something like that, or it would go something like that. And once again, to decide which of these it is, you would actually want to try out a few values. So I encourage you to after this video, try that out on yourself and try to figure out what. Let f of x equal a times x to the n plus bx plus 12 over c times x to the m plus dx plus 12, where m and n are integers and a, b, c, and d are unknown constants. All right, this is interesting. which of the following is a possible graph of y is equal to f of x? And they tell us that dashed lines indicate asymptotes. And they give us 4 choices here. And so I encourage you, like always, pause this video, give a go at it. See if you can figure out which of these graphs could be the graph for y equals f of x, where they've given us this information about f of x. All right, now let's work through this together. Now this is really interesting. It's, they didn't give us a lot. They didn't even tell us what the exponents on x are. They haven't even given us the coefficients. All they've told us is this 12 here. So this 12 looks like a pretty big clue. So what can that tell us? The way they've written it, we really can't deduce any zeros for the function. We really can't deduce what x values make the numerator equal 0 or what x values make the denominator equal 0. So it's going to be hard for us to deduce what are the zeros of the function or what are the removable discontinuities or what are the vertical asymptotes. But just this 12 sitting here does tell us one thing. What happens when x equals 0? Because when x equals 0, every other term in this rational expression is just going to be equal to 0. And so we can figure out f of 0. F of 0 is going to be equal to, well, a times 0 to the n, well, that's just going to be 0, plus b times 0, well, that's just going to be 0, plus 12, over c times 0 to the m power, well, that's just going to be 0. D times 0 is going to be 0, and then we have our 12 there. So we're actually able to figure out what f of 0 is. It's 12 over 12, or 1. So we actually know the y-intercept for this function. Let's see if that's enough information for us to figure out if any of these choices could be the graph of y equals f of x. So let's see here. So choice A, our y-intercept is at 2. When x equals 0, our graph goes through 2. So we can rule that out. The y-intercept needs to be 1. So we can rule out, let's see, choice B does have a y-intercept, it looks like, just eyeballing it, at 1. X equals 0, y is 1, so this looks interesting. Choice C has its y-intercept at y is equal to -1. So once again, we can rule that out. And choice D has no y-intercept at all. So that was enough information, and lucky for us because they really didn't give us a lot more information than just being able to evaluate f of 0. We weren't able to figure out any of the other, the zeros or the vertical asymptotes or the removable discontinuities. So we definitely feel good about that choice. Information, and lucky for us because they really didn't give us a lot more information than just being able to evaluate f of 0. We weren't able to figure out any of the other, Let f of x equal -x squared plus ax plus b over x squared plus cx plus d, where a, b, c, and d are unknown constants. Which of the following is a possible graph of y is equal to f of x? And they tell us dashed lines indicate asymptotes. So this is really interesting here. And they give us 4 choices. We see 3 of them right now. And then if I scroll a little bit over, you can see choice D. And so I encourage you to pause the video and think about how we can figure it out, because it is interesting, because they haven't given us a lot of details. They haven't given us what these coefficients or these constants are going to be. All right, now let's think about it. So one thing we could think about is horizontal asymptotes. So let's think about what happens as x approaches positive or negative infinity. Well, as x approaches infinity or x approaches negative infinity, f of x is going to be approximately equal to, well, we're going to look at the highest degree terms because these are going to dominate as the magnitude of x, the absolute value of x, becomes very large. So f of x is going to be approximately -x squared over x squared, which is equal to negative, or another way to think about it, this is the same thing as -1. So f of x is going to approach -1 in either direction as x approaches infinity or x approaches negative infinity. So we have a horizontal asymptote at y equals -1. Let's see, choice A here, it does look like they have a horizontal asymptote at y is equal to -1 right over there. And we can verify that because each hash mark is 2. We go from 2 to 0 to -2 to -4. So this does look like it's at -1. So just based only on the horizontal asymptote, choice A looks good. Choice B, we have a horizontal asymptote at y is equal to +2. So we can rule that out. We know that our horizontal asymptote as x approaches positive or negative infinity is at -1, y equals -1. Here, our horizontal asymptote is at y is equal to 0. The graph approaches the x-axis from either above or below. So it's not, the horizontal asymptote is not y equals -1, so we can rule that one out. And then similarly, over here, our horizontal asymptote is not y equals -1. Our horizontal asymptote is y is equal to 0. So we can rule that one out. And that makes sense because really they only gave us enough information to figure out the horizontal asymptote. They didn't give us enough information to figure out how many roots or what happens in the interval and all of those type of things, how many zeros and all of that, because we don't know what the actual coefficients or constants of the quadratic are. All we know is what happens as the x squared terms dominate. This thing is going to approach -1, and so we pick choice A. We're told let f of x equal g of x over x squared minus x minus 6, where g of x is a polynomial. Which of the following is a possible graph of y equals f of x? And they give us 4 choices. The 4th choice is off right over here. And like always, pause the video and see if you can figure it out, or if you are having trouble with it as I start to think about it with you, pause it at any time if you feel inspired. It's really important to try to engage in the problem as opposed to just watch me do it. But let's start tackling this now together. So this is interesting. They don't give us a lot of information about f of x. In fact, we don't know what the numerator is. We just know that it is a polynomial. Well, that's somewhat valuable. But they do give us the denominator, and so we could think about what are the interesting numbers, what are the interesting x values for the denominator. In particular, what x values will make the denominator equal to 0. And to do that, we can factor out the denominator. So let's see, the coefficient on the first degree term is essentially -1. We could write -1 there if we want. And the constant is -6. So if we want to factor that, we could say, well, what two numbers, their product is -6, and they add up to -1? Well, -3 times +2 is -6, and -3 plus 2 is equal to -1. So I can rewrite f of x. I can say that f of x is equal to g of x over x minus 3 times x plus 2. So the denominator equals 0 for x equals 3 or x equals -2. That's when the denominator is 0. So 0 denominator. I'll just write it like that. And so if something makes the denominator equal to 0, that tells us that we're either going to have a vertical asymptote at that point, or we're going to have a removable discontinuity at that point. And the way that would be a removable discontinuity, let's say if we had a removable discontinuity at x equals 3, well, that means that g of x could be factored into x minus 3 times a bunch of other stuff. If that was the case, then x equals 3 would be a removable discontinuity. If x equals 3 does not make g of x equal 0, so for example, if g of 3 does not equal 0 or g of -2 does not equal 0, then these would both be vertical asymptotes. So let's look at the choices here. So in choice A, we have one vertical asymptote. That vertical asymptote is at x equals -2. So it seems this line, let me draw this line here. This vertical asymptote right over there, that is the line x is equal to -2. So at least it seems to be consistent with that over there. But what about x equals 3? This one seems completely cool. This graph is defined at x equals 3. X equals 3 is right over there, and it seems to be defined there. And this f of x is clearly not defined at x is equal to 3. Because when x equals 3, the denominator is 0, and dividing by 0 is not defined. So even though this has one vertical asymptote at an interesting place, we're going to rule it out because this graph is defined at x equals 3, even though f of x is not. We would need to see either a vertical asymptote there, or a removable discontinuity. All right, here we have a vertical asymptote at x is equal to -2. And then we have another vertical asymptote at x is equal to +4. So that doesn't make sense either. This one, just like the last one, is actually defined at x equals 3. We see at x equals 3, the function is equal to 0. But this function, f of 3, is not equal to 0. F of 3 is undefined. We're dividing by 0. So we can rule this out. Once again, at x equals 3, we need to see the removable discontinuity or a vertical asymptote because we're not defined there. All right, let's see. Choice C, we see a vertical asymptote at x is equal to -2. So that looks pretty good. And we see a removable discontinuity at x equals 3. So this graph is not defined for x equals 3 or for x equals -2, which is good because f is not defined at either of those points because at either of those x values, our f's denominator is equal to 0. So this one looks quite interesting. And this would be consistent. This one would be consistent with f of x being something of the sort of, so the denominator we already know, x minus 3 times x plus 2. And in the numerator, we would have, since x minus 3 is not a vertical since x equals 3 isn't a vertical asymptote, it's a removable discontinuity, we must be able to factor, for this one, g of x into x minus 3 times something else. So that's consistent with this one over here. So I like this choice. Now let's look at this choice, choice D. Choice D has two vertical asymptotes. One at x is equal to -1. This is -2. So this x equals -1, and this is x is equal to 6. Neither of them are what coincide with what make our denominator equal 0. So we can rule this out as well. So we can feel really good about choice C. So we're told let f of x equal 2x squared minus 18 over g of x, where g of x is a polynomial. And then they tell us which of the following is a possible graph of y is equal to f of x. And they give us 4 choices here. And like always, I encourage you to pause the video and see if you could give a go at it. Look at our f of x and then think about which of these graphs actually match up or could match up to that f of x. All right, now let's work through this together. And they don't give us a lot of information. They don't tell us anything about the denominator of this rational expression. But they do tell us its numerator. And like we've seen before, it's useful to factor the numerator and see at what x values do interesting things happen. In particular, at what x values does the numerator equal 0? So if we factor the numerator up here, we could rewrite f of x as being equal to, let's see, we could factor out a 2 out of the numerator. So it's 2 times x squared minus 9, and that's all going to be over g of x. We don't know what the denominator is. We just know that it's a polynomial. Now let's see, here in the numerator, x squared minus 9, you might recognize that as a difference of squares, so we can factor that further. So we still have that original 2, and it's going to be x plus 3 times x minus 3. We've seen that multiple times. If that looks unfamiliar to you, I encourage you to watch the video on differences of squares or factoring polynomials. X squared minus 9 is the same thing as x squared minus 3 squared. So it's x plus 3 times x minus 3, and then all of that is still going to be over g of x. So the first thing that we might realize, okay, when does our numerator equal 0? Well, when x is equal to -3 or when x is equal to +3. If x is equal to -3, this expression is going to be 0. If x is equal to +3, this expression is equal to 0. So you might just say, well, maybe we have zeros at plus or minus 3. So maybe at x is maybe f of -3 is equal to 0 and f of +3 is equal to 0. Those values sure look like they make the numerator equal to 0. And then we look at our choices. And when we look at our choices, this choice A does seem to have a 0 at +3, but it doesn't have one at -3. It has a vertical asymptote at -3. So that seems a little bit confusing. This choice B does have a 0 at +3, but it has nothing going on here or nothing interesting going on at -3. It defines -3. It doesn't even have a vertical asymptote there. So once again, this looks a little bit perplexing. Choice C has a removable discontinuity at +3, and then it has a vertical asymptote at -2. So once again, this doesn't have anything interesting going on at x is equal to -3. So still a little perplexing. And this one has zeros at +6 and -6. So none of the choices have zeros at both x equals +3 and x equals -3. So what's going on? Well, what we need to realize is just because something makes the numerator equal to 0 doesn't mean that it's definitely going to be a 0 for that function. And you might say, well, how can that be? Well, think about situations in which those values would also make the denominator equal to 0. So let me write out some potential f of x's here. So we just know that g of x is a polynomial. So f of x could be, we know the numerator, 2 times x plus 3 times x minus 3 over, well, let's just say g of x is, I'm just going to make up something. G of x is equal to x plus 1. Well, in this situation, none of the values that make the numerator equal 0 make the denominator equal 0. So this is a situation where you would have two zeros at x equals +3 and x equals -3. So this would be the two zeros. Two zeros. And so let's look at another situation. Let's look at a situation where f of x is equal to, we know the numerator, x plus 3 times x minus 3. And let's say that we do have, let's say that one of those x values, positive or -3, do make the denominator equal to 0. So let's say x plus 3 and then say times x plus 1. Well, you see here, now since x plus 3 is both in the numerator and the denominator, you could divide x plus 3 divided by x plus 3, they cancel out. And here x equals -3 would be a removable discontinuity. So this would have 0, 0 at x equals 3 and a removable discontinuity at x equals negative 3. And so those values that make the numerator equal to 0, we now see could be a 0, or it could represent a removable discontinuity. And here I just picked a removable discontinuity to be at negative 3. It could be, or it could be the other way around, or it could be at both values. If this was x plus 3 times x minus 3 over x plus 3 times x minus 3, then you would have a removable discontinuity at both x is positive 3 and negative 3. And then you could go even further. F of x could look like this. It could be 2 times x plus 3 times x minus 3 over x plus 3 squared, and I'll just make up another expression here, x plus 1. So what's going to happen here? Even if you divide the numerator and the denominator by x plus 3, you're still going to have one x plus 3 left over in the denominator. That could cancel with one of the x plus 3s, but you're still going to have an x plus 3. And so in this case, you would have a vertical asymptote. So in this case, you would have a 0 at x is equal to 3, and you would have a vertical asymptote. I'll just shorten it, shorthand. You'd have a vertical, I'll just write it out. A vertical asymptote at x is equal to negative 3. So these particular examples that I just showed you that any value that makes the numerator equal 0 aren't necessarily zeros for the function. They could be zeros, they could be removable discontinuities, or they could be vertical asymptotes. But they would all occur at x is equal to positive or negative 3. So with that lens, now let's look at the choices again. So choice A has a 0 at x equals positive 3, and it has a vertical asymptote at x equals negative 3. So that's actually very consistent with this situation that I just described. So choice A actually is looking pretty good. Choice B has a 0 at x equals 3, but its vertical asymptote looks like it's at x equals 2, and nothing interesting is happening at x equals negative 3, so we can rule that out. So now if you look at choice C, you have a removable discontinuity at x equals positive 3, which is completely possible. We've seen that situation where something that makes the numerator equal 0 could be a removable discontinuity if you have that same expression in the denominator. But then the vertical asymptote isn't at x equals negative 3, it's at x equals negative 2. So that rules it out. Once again, nothing interesting happening at x equals negative 3. And here you have two zeros, but they're not at x equals positive or negative 3, they're at x equals positive or negative 6. So we can definitely rule that one out. So we should feel pretty good about choice A. So up here we are multiplying two rational expressions, and here we're dividing one rational expression by another one. And what I encourage you to do is pause these videos and think about what these become when you multiply them out, and maybe you simplify it a little bit. And I also want you to think about what constraints do you have to put on the x values in order for your resulting expression to be algebraically equivalent to your original expression. So let's work it out together just so you realize what I'm talking about. So this is going to be, in our numerator, we are going to get 6x to the third power times 2. In our denominator, we're going to have 5 times 3x. And we can see both the numerator and the denominator are divisible by x. So let's divide the denominator by x. We get 1 there. Let's divide x to the third by x. We get x squared. And we can also see that both the numerator and denominator are divisible by 3. So divide 6 by 3, you get 2. Divide 3 by 3, you get 1. And we are left with 2x squared times 2, which is going to be 4x squared, over 5 times 1 times 1, over 5. And we could also write that as 4/5 x squared. Now, if someone just presented you on the street with the expression 4/5 x squared and say, for what x's is this defined? You can say, well, I could put any x here. X could be 0, because 0 squared is 0, times 4/5 is just going to be 0, so it seems to be defined for 0. And that is true. But if someone says, how would I have to constrain this in order for it to be algebraically equivalent to this first expression? Well, then you'd have to say, well, this first expression is not defined for all x. For example, if x were equal to 0, then you would be dividing by 0 right over here, which would make this undefined. So you could explicitly call it out, x cannot be equal to 0. And so if you want this one to be algebraically equivalent, you would have to make that same condition. X cannot be equal to 0. Another way to think about it, if you had a function defined this way, if you said f of x is equal to 6x to the third over 5 times 2 over 3x, and if someone said, well, what is f of 0? You would say f of 0 is undefined. Undefined. Why is that? Because you put x equals 0 there, you're going to get 2 divided by 0, and it's undefined. But if you said, okay, well, can I simplify this a little bit to get the exact same function? Well, we're saying you can say f of x is equal to 4/5 times x squared. But if you just left it at that, you would get f of 0 is equal to 0. So now it would be defined at 0. But then this would make it a different function. These are two different functions the way they're written right over here. Instead, to make it clear that this is equivalent to that one, you would have to say x cannot be equal to 0. Now these functions are equivalent, because now if you said f of 0, you'd say, all right, x cannot be equal to 0. This would be the case if x is anything other than 0, and it's not defined for 0, and so you'd say f of 0 is undefined. So now these two functions are equivalent, or these two expressions are algebraically equivalent. So thinking about that, let's tackle this division situation here. So immediately when you look at this, you say, well, what are constraints here? Well, x cannot be equal to 0, because if x was 0, this 5x to the 4th over 4 would be 0, and you'd be dividing by 0. So we can explicitly call out that x cannot be equal to 0. And so if x cannot be equal to 0 in the original expression, if the result, whatever we get for the resulting. So what I have here is an expression where I'm multiplying rational expressions, and we want to do this multiplication and then reduce to lowest terms. So if you feel so inspired, I encourage you to pause this video and see if you can have a go at that. All right, now let's work through this together. So multiplying rational expressions like this, it's very analogous to multiplying fractions. For example, if I were to multiply 6/25 times 15 over 9, there's a few ways you could do it. You could just multiply 6 times 15 in the numerator and 25 times 9 in the denominator. But the way that many of us approach it so that it's easier to reduce to lowest terms is to factor things, to realize that, look, 6 is 2 times 3, 9 is 3 times 3, 15 is 3 times 5, and 25 is 5 times 5. And then you can realize in your eventual product, you're going to have a 5 in the numerator, 5 in the denominator. 5 divided by 5 is 1, 3 divided by 3 is 1, and then 3 divided by 3 is 1. And so all you'd be left with is that 2 and then that 5. So this is going to be equal to 2/5. So we'll do the analogous thing here with these rational expressions. We're going to factor them, all of them, in the numerators and the denominators, and then we'll see if we can divide the numerator and the denominator by the same thing. Now, the one thing we have to make sure of as we do that is we keep track of the domain, because these rational expressions here, they might have x values that make their denominators equal to 0. And so even if we reduce to lowest terms and we get rid of those expressions, in order for the expressions to be the same expression, we have to constrain the domain in the same way. So let's get started. So this is going to be equal to, I'll just rewrite everything, x squared minus 9. How do we factor that? Well, that's going to be a difference of squares. We could write that as x plus 3 times x minus 3. And then that is going to be over this business. And let's see, 5 squared is 25. Negative 5 plus negative 5 is negative 10. So this is going to be x minus 5 times x minus 5. If what I'm just doing here with the factoring is not making sense, I encourage you to review factoring on Khan Academy. And then we multiply that times, let's see, in this numerator here, I can factor out a 4. So that's going to be 4 times x minus 5, which is going to be useful. I have an x minus 5 there, x minus 5 there. And then that's going to be over, let's see, this expression over here, 2 plus 3 is 5, 2 times 3 is 6. So it's going to be x plus 2 times x plus 3. Now before I start reducing to lowest terms, let's think about the domain here. And the domain is going to be constrained by things that make these denominators equal to 0. So the domain would be all real numbers except x cannot equal 5. Let me write it over here. X cannot equal 5. Because if that happened, then this denominator would be equal to 0. X cannot be equal to negative 2. X could not be equal to negative 2 because that would make the denominator here 0, which would make the denominator here 0. And x cannot be equal to negative 3. So the domain is constrained in this way. And we have to carry this throughout. No matter what we do to the expression, this is the constraints on our domain. With that out of the way, now we can reduce to lowest terms. So x, we have an x plus 3 in the numerator, x plus 3 in the denominator, x minus 5 in the numerator, x minus 5 in the denominator. And I think we've gone about as far as we can. And so when we multiply the numerators, we are going to get, this business is going to be 4 times x minus 3, 4 times x minus 3 over, we have an x minus 5 here, x minus 5, and then we have an x plus 2. We have an x plus 2. And we could leave it like this if you want. In some cases, people like to multiply the things out, but we're done. We've just finished multiplying these rational expressions. And we have to remind ourselves that x cannot be equal to any of these things. Now, the way that we've simplified it, we still have an x minus 5 right over here. So it might be redundant to say that x cannot be equal to 5, because that's still the case in our reduced terms expression here. And that's true also of the x cannot be equal to negative 2. We still have an x plus 2 here. So still, even in this expression, it's pretty clear that x cannot be equal to negative 2. But that x cannot equal negative 3 isn't so obvious when you just look at this expression. But in order for this expression to be completely equivalent to the original, it has to have the same domain. And so you might want to explicitly say that x cannot be equal to negative 3 here. You could also say the other two, but that's still very clear when you look at this expression.
Find the difference, express the answer as a simplified rational expression, and state the domain. So we have two rational expressions, and we're subtracting one from the other. And just like when we first learned to subtract fractions or add fractions, we have to find a common denominator. And the best way to find a common denominator, if we're just dealing with regular numbers or with algebraic expressions, is to factor them out and make sure that our common denominator has all of the factors in it. That'll ensure that's divisible by the two denominators here. So this guy right here is completely factored. He's just a plus 2. This one over here, let's see if we can factor it. A squared plus 4a plus 4. Well, you see the pattern that 4 is 2 squared. 4 is 2 times 2. So a squared plus 4a plus 4 is a plus 2 times a plus 2, or a plus 2 squared. So we say it's a plus 2 times a plus 2. That's what a squared plus 4a plus 4 is. So this is obviously divisible by itself. Everything is divisible by itself, except I guess for 0. It's divisible by itself. And it's also divisible by a plus 2. So this is the least common multiple of this expression and that expression. And it could be a good common denominator. So let's set that up. This will be the same thing as being equal to this first term right here, a minus 2 over a plus 2, a minus 2 over a plus 2. But we want the denominator now to be a plus 2 times a plus 2. We want it to be a plus 2 squared. So let's multiply this numerator and denominator by a plus 2, so its denominator is the same thing as this. So let's multiply both the numerator and the denominator by a plus 2, And we're going to assume that a is not equal to negative 2. That would have made this undefined. It would have also made this undefined. So throughout this whole thing, we're going to assume that a cannot be equal to negative 2. The domain is all real numbers. A can be any real number except for negative 2. So the first term is that. Extend the line a little bit. And then the second term doesn't change because its denominator is already the common denominator. So minus a minus 3 over, and we could write it either as a plus 2 times a plus 2, or as this thing over here. Let's write it in the factored form. It'll make it easier to simplify later on. A plus 2 times a plus 2. And now, let's set this up like this. Now, before we add the numerators, it'll probably be a good idea to multiply this out right there. But let me write the denominator. We know what that is. It is a plus 2 times a plus 2. Now, this numerator, if we have a minus 2 times a plus 2, we've seen that pattern before. We can multiply it out if you like, but we've seen it enough, hopefully, to recognize that this is going to be a squared minus 2 squared. Or this is going to be a squared minus 4. You can multiply it out. The middle terms cancel out. The negative 2 times a cancels out with the a times 2, and you're just left with a squared minus 4. That's that over there. And then you have this. You have minus a minus 3. So let's be very careful here. You're subtracting a minus 3. So you want to distribute the negative sign or multiply both of these terms times -1. So you could put a minus a here, and then negative 3 is plus 3. So what does this simplify to? You have a squared minus a plus, let's see, -4 plus 3 is -1. All of that over a plus 2 times a plus 2. Or we could just write that as a plus 2 squared. Now, we might want to factor this numerator out more to just make sure it doesn't contain a common factor with the denominator. The denominator is just two a plus 2's multiplied by themselves. And you can see from inspection, a plus 2 will not be a factor in this top expression. I mean, if it was, this number right here would be divisible by 2. It's not divisible by 2. So a plus 2 is not one of the factors here. So there's not going to be any more simplification, even if we wanted, even if we were able to factor this thing in the numerator out. So we're done. We have simplified the rational expression, and the domain is for all a's except for a cannot, or all a's given that a does not equal -2. All a's except for -2. And we are done.
Alright guys, this is what we have learned so far. On this video, we have learned about the rational functions and how can we do some operations with it. And that's it. I will see you guys in the next video. Bye.